So let's discuss a problem from GATE 2021 Physics, and this is from Classical Mechanics, and it is related to the spherical galaxy and orbital velocity of the star. It's as a function of distance from the galaxy. So let's have a look at the problem. So consider a spherical galaxy of total mass capital M, radius R. So they have given us a spherical galaxy. So a galaxy is nothing but group of stars. So the total mass of that galaxy is M, which means mass of all the stars present in the galaxy is M. So suppose this is, so it's just a group of stars. Galaxy is nothing but a group of stars, different stars of appropriate colors, like that. So each star would be having its own mass. So total mass of the galaxy is nothing but mass of all these stars, and it is of radius capital R, having uniform matter distribution. So uniform matter distribution, actually you cannot say that the stars are present at uniform distance and of equal masses. Some stars might be very massive, some stars may be very less, some stars might be far away from very much more far away from other stars. Sometimes the stars might be gathered together, so like that. Actually, in general, uneven distribution of mass will be there. So here we have to consider as if it is a uniform distribution of mass, equal distribution of mass. So in this idealized situation, so they only have given it is an idealized situation. Generally, such type of galaxy would not exist in which uniform distribution of stars take place. Mm, if we look from the localized view, maybe from overall average view, we can make an average also, but in general, star masses are just scattered away. So next thing is, in this idealized situation, the orbital speed v of a star of mass m is much more less than capital M. So here they have given this condition. We need to find the orbital speed of star. Some star we have to take in that galaxy. It might be at the edge of the galaxy, or it may be outside of the galaxy, or it may be residing anywhere inside the galaxy in general. And they have also mentioned M is much more less than capital M, which means if we have taken that star out of, if you have taken that particular star out of that galaxy, even then the mass of the galaxy would be uh, nearly equal to M, capital M. So as a function of distance also, this condition is very important while considering the conditions. So even we have, so it is just like taking 1 from 1 lakh or 1 crore rupees. If we subtract 1 from 1 crore rupees, it doesn't matter much, but that only if we subtract 1 from 10 rupees, it matters a lot. So this is like subtracting 1 rupee from 1 crore, like that. So just removing a little bit of mass from the galaxy, so mass would remain constant. So as a function, now the orbital speed v of a star as a function of distance r from the galactic center is, so we need to see which graph best describes the variation of orbital velocity of the star from the galactic center. So that is the thing we needed to find out. So these are the options A, B, C and D. So we need to find out. For that, first we need to look at the relationship between orbital velocity and distance from the galactic center. So here it is given for a star orbiting at almost edge of galaxy and beyond. So let us uh, suppose this is some galaxy, just imagine like that. So these are nothing but a group of stars is nothing but a galaxy. So this is some spherical galaxy, like that let us consider. So this entire thing is a galaxy, and So it is spherical in shape like that. Let us consider spherical and even distribution of masses. So these are star. It is a galaxy. So for a star orbiting at almost edge of the galaxy, so stars like this. So this is at the edge of the galaxy, or we can take the star which is almost outside of the galaxy like this. It is remaining almost outside of the galaxy. So for this star, so r is greater than r, where capital R is the radius of the galaxy. So this is the radius of the galaxy, capital R. And if we take suppose a star outside, still more outside, nearly outside of the galaxy, like here if we consider, so that is nothing but capital R in this case. In this case, this is capital R, small r. So which is here, we can see that small r is greater than capital R. Capital R is the radius of the galaxy. So but star is residing almost out of the galaxy, some a little bit away from the galaxy. So for such a case, what would happen is mv square by r is equal to gmm by r square. That is, as the star is orbiting about the galactic center, so it would be keeping on orbiting about this galactic center wherever it is. So like that, the process of orbiting, so what happens, uh, so if this is a star orbiting about the galactic center, so uh, towards the galactic center, force of attraction would be acting because of the, that is, all the other stars. So let us suppose the star is this, not this. So let us suppose the star is orbiting about this galactic center. So here this star is faced with the uh, gravitational pull because of this entire mass, entire galaxy. So that is, gravitational force would be acting because of the group of masses. All these masses put together would be pulling the star towards the galactic center. So hence that force is gmm by r square. That's the force of attraction between two masses. Here capital M is the mass of the galaxy and small m is the star just outside the galaxy. Or so that's why we have to consider that small m is much more less than capital M. So even though we have to, actually this star belongs to this galaxy only. So if we remove the mass of that star from the galaxy also, it doesn't matter. So in that case, what happens is, uh, so gravitational force would be acting towards the center, gravitational force, that is gmm by r square, between two masses, that is galaxy and star. And because of rotational motion, orbital motion of the star, centrifugal force would be acting in outward direction. So when both of these gravitational and centrifugal force uh, are balanced, then the star would remain at that particular orbit, or else it may fall into the galaxy center of the galaxy if gravity is, if this gravitational force is more, or it may move away from the galaxy if centrifugal force is more. So this is the formula for centrifugal force, mv square by r, the speed with which the galaxy is moving. And now here if we see, here r would get cancelled, would get cancelled. What would remain is v is also root gm by r. This is the condition, required condition for, this is the velocity of the star. And for when r is greater than capital R, so here in general g and m are constant. G is gravitational constant, m is considered to be constant because the mass of that galaxy would remain constant. So that in overall, if we see, v is inversely proportional to square root of r outside the galaxy, means the star which is almost outside at the edge of the galaxy. So that means r greater than capital R. So this is the condition. So for this so this is the condition for outward thing. Next, so the graph would be like, we know that square root of 1 is 1, square root of 1 is 1, and square root of 4 if we consider, that is 2, that is 1 by 2. another value is 1 by 2. So what is happening here, as the r value is going on increasing, v value is going on decreasing. So here especially the graph would be like this. So it is a decrease, it would be decreasing in this manner. So if r is greater than r, the graph would be like this. And next what we need to see is, if the star is somewhere inside the galaxy. So if it is residing inside the galaxy, that is stars like this, for them this is the r. So here we can see clearly that in this case, uh, r is less than capital R, that is as the star is residing inside the galaxy. Then for that case also, if we apply the same formula, mv square by r, mass of that star, orbital velocity of that particular star, and its distance from the galactic center, is equals to gm by r square, m dash m by r square. So here we are taking m dash because as here the star is residing within inside the galaxy. So here the stars are remaining. So it is, the background itself is like a group of stars here, the page background. So suppose this is the star we are going to study. So this star is residing inside the galaxy. So this star faces gravitational pull because of these stars only inside inside that star. So the actually force of gravitational pull is towards the center of the galaxy. So only these masses would be pulling this star towards the center of the galaxy, but not these masses present outside the galaxy. They won't attract that, they won't pull that, they won't apply force on this particular star. It is just like a uniform mass distribution. So it is only uh, acted by just like a body, gravity acting on a body outside the earth, gravitational pull acting on a body which is moving nearer to the center of the earth. So it is just like that, similarly just like that, but only case is here the body is replaced with star, and galaxy, that is earth is replaced, earth's surface is replaced with that of galaxy, that's it. So only this mass contributes to the gravitational force. Now we need to see the gravitational force because of this mass, that is only we need to find out this entire mass, what is the mass that is attracting. So in order to do so, we need to find out the density of the galaxy, that is m dash is nothing but density of the galaxy, and that means mass per unit volume of the galaxy multiplied with overall volume. So this is the overall volume that is attracting this star. So density of the galaxy is nothing but volume. In unit volume, how much mass is there? In this much amount of volume, how much mass is there? That is nothing but m dash. So here if we see, so that is the density of this galaxy is nothing but total mass by total volume. Total mass of the galaxy is nothing but capital M. Volume of the galaxy, as it is a spherical galaxy, they have given in the question. So 4 by 3 pi r cube. And volume is nothing but as the star is at a distance smaller from this, so only this volume, so this volume is nothing but 4 by 3 pi r cube, as the star is at a distance smaller. Now 4 by 3 pi, this one would get cancelled. What would remain is m r cube by n small r cube by capital R cube, and that is nothing but v square is nothing but here m, this is from this formula, v would get cancelled, r would get cancelled, v square is nothing but gm dash by r. So this is gm dash by r. So in the place of m dash we need to substitute this. So after substituting that in the place of m dash, m r cube by capital R cube. So here gm and r cube has to be taken aside, and r would get cancelled and we will get r square. So this is the thing, and next we need to take the square root to that side. So taking that square root to that side, we would have root gm by r cube, and square root of r square is nothing but r. That means here gm by r cube is almost a constant, gravitational constant, mass of the galaxy, radius of the galaxy. And in overall we can see that v is directly proportional to r, that is y, just like y is directly proportional to x, that is y is equals to mx, which is an equation of a straight line passing through the origin. So here when r is less than small r is less than capital R, we would have this condition. And so we would have a straight line for this condition. And another important point is when small r is equal to r, that means when the star is residing almost at the edge of the galaxy, when it is at the edge of the galaxy equal to the radius of the galaxy. So in that case, this is the case. So here r square has to be replaced with capital R square. So r square would get cancelled, root gm by r. So this is the value, root gm by r. This value is also very important. So based on this, now finally, based on this conditions, that is, so based on this condition especially, so this condition v is greater than r, and v is equals to gm by r at small r is equals to capital R. And finally based on this condition, that is, so this condition, based on this condition, so the appropriate answer, so here graph would be reducing, so that is when r is greater than capital R. So the appropriate answer is A. So here you can see when r is less than capital R, it is a straight line, just we have seen here. When r is less than capital R, v is directly proportional to r, and root gm by r, when r is equal, small r is equals to capital R. So when small r is equals to capital R, it is root gm by r. So small r at r. And next is when this is the case when r is greater than capital R. So that is 1 by root 2. Just we have seen here. 1 by root r. So it would go on increasing as r increases, velocity v goes on decreasing. So this is the appropriate graph for this question. So this is the appropriate answer for this question. That means here if we see, as the star moves away when it moves more far away from the galaxy, its orbital velocity decreases because gravitational pull would decrease, because it is force of attraction is inversely proportional to 1 by r square. And here if we see, as the star is moving away from center of the galactic center, more mass would be attracting. The more masses would be residing inside D, because if it acts as a single system, so more stars would be attracting it, more is the mass, more is the gravitational force, and more speed it has to catch up in order to prevent from falling into the center of the galaxy. So that only it is very, if it is very nearer to the galactic center, so only little masses would be attracting it. However, but if there is a black hole at the center of galaxy, its velocity would be really maximum. Slowly the star decomposes and it splits up and it falls into the black hole. So this is the problem regarding spherical galaxy orbital velocity. So thank you.